Welcome to today's deep dive. If you're the kind of learner who loves a good aha moment, and you just want a shortcut to being well-informed without getting completely bogged down in information overload, well, you are in the exact right place.
Yeah, absolutely. We've got a really great one today.
We do. Today, we are taking you inside the hidden brain of modern live events. So just picture a classic, massive live soundboard. You've probably seen one sitting out there in the middle of a concert arena.
Oh, yeah. Surrounded by barricades, usually.
All right, barricades, security guards. It's like the size of a dining room table covered in strips of glowing tape. And it's just this incredibly intimidating sea of hundreds of faders, blinking lights, complicated knobs.
It looks like a spaceship console.
Exactly. And for decades, that giant, heavy piece of hardware was the undisputed solitary command center of the entire audio operation. I mean, it was a completely closed system.
It was essentially a fortress. I mean, everything, every microphone, every speaker, every single command, it all had to run physically through that specific surface.
Wow.
Yeah. So if you wanted to control the mix, you literally had to stand in front of that specific piece of metal and plastic. There was no way around it.
But our mission today is to completely shatter that image for you. We've gathered a stack of really fascinating sources detailing the architecture of the dMix 128 digital audio mixer, and specifically its integration with a protocol called Open Sound Control, or OSC.
Right. OSC. It's a total game changer.
It really is, because when you dig into this material, you realize that the reality of professional audio has totally shifted. The absolute best audio systems today, they aren't judged by how heavy they are.
Or how many physical faders they can cram onto a desk.
Exactly. They're judged by how easily they can be automated, expanded, and integrated into a broader network. So we're looking at a transformation where the mixer is no longer the static box of knobs. It's a dynamic, open networked brain.
And that shift, I mean, it changes everything. It changes who has access to the audio, how shows are designed, and fundamentally just how humans interact with complex acoustics.
Yeah.
So we've got a really interesting roadmap to explore this today. We need to look at the language that makes this possible first. And then crucially, the unique internal architecture of the dMix 128 that keeps everything from just descending into total chaos when, multiple devices try to control it at the exact same time.
Okay, let's unpack this with a mental image for you. If a traditional mixer is like a locked vault where only the manufacturer holds the key and they dictate exactly how you're allowed to interact with the money inside, the dMix 128 is designed a lot more like an open concept commercial kitchen.
Oh, I like that analogy.
Right. It's built from the ground up so that multiple chefs can safely cook at the same time. They're using their own distinct tools, but they aren't constantly bumping elbows or, burning the building down.
Yeah, and what makes that open kitchen possible is the language those chefs are speaking to each other. Because before we even touch the internal guts of the mixer, we really have to look at how outside devices communicate with it.
Which brings us to OSC.
Yeah, exactly. Open sound control. It's one of those totally invisible technologies that just quietly powers the background of almost every massive live event you attend.
It's everywhere.
It really is. It's a communication protocol originally designed for music, media, lighting, and interactive performance systems. And the crucial detail here, the thing that really matters, is that it runs over standard computer networks.
Wait, like regular home internet network?
Yeah, we're talking about the exact same everyday Ethernet cables and Wi-Fi networks you use in your house to, watch Netflix.
That is wild, which is already a huge conceptual leap from the old days, right? Running a massive, thick copper audio snake hundreds of feet across some sticky bar floor.
The worst.
I want to contextualize this for anyone who has maybe dabbled in music production. How does OSC actually compare to something we might already know, like MIDI? Because, MIDI has been the absolute bedrock standard for musical communications since, the early 1980s?
Yeah, early 80s. And look, MIDI is brilliant for what it was built to do.
Yeah.
Which is primarily triggering musical notes and basic performance controls on electronic keyboards.
Right.
But because it was invented in an era of, honestly, extreme technological constraints, it can be highly cryptic.
Oh, yeah.
You're dealing with this tiny data pipe. It's limited to values from 0 to 127, and you have to use these obscure things called control change numbers.
Oh, man, the control change numbers. Right, so if you want to tell a mixer to change a specific EQ parameter using MIDI, you can't just type change the EQ, you often find yourself just squinting at a massive, confusing chart in the back of some huge paper manual.
Exactly.
Just trying to figure out if, like, Control Change 71 is the filter resonance or the panning. It's nightmare.
It feels like programming in assembly language.
Yeah.
It's not intuitive at all. OSC, on the other hand, was designed from the ground up to be open-ended and, most importantly, human-readable.
Human-readable. Okay.
Yeah, it carries named commands, highly structured messages, and these really specific, high-resolution numeric values in a way that actually makes semantic sense to a person reading it.
Well, let's look at the actual structure, because the materials provide a crystal clear example of this. An OSC message basically has two halves, right?
Right.
You have an address, which is the specific thing you want to target and control, and then you have a value, which is the new setting you want to apply to it.
Spot on.
So instead of sending a cryptic MIDI code and just hoping it aligns, you send a string that looks almost like a website URL. The sources say it looks like this: /che/01/mix/fader space 0.5.
Exactly. You don't need a decoder ring to understand the intent there.
No, not at all.
It explicitly says in plain text, go to channel 1, find the mix fader, and set it to 0.5, or, exactly halfway up.
It's the difference between having to type in a bizarre string of command line code just to turn on a lamp versus just telling your smart home system, hey, living room lights 50%.
That's a perfect way to put it. It's direct, it's semantic, and it's infinitely scalable. And because it runs over a standard computer network, you aren't limited to a single keyboard plugged into the back.
Right.
You can have a touchscreen controller app on an iPad, a media server running video, a lighting console, or even just a custom automation script written by some programmer. And all of them can be sending these very clear, human-readable commands over Wi-Fi or Ethernet to the mixer simultaneously.
I love the flexibility there. But I've got to push back on something I noticed in the networking specs from the sources.
Okay.
The dMix 128 supports sending these OSC messages over two different network protocols. It lists UDP on port 1023 and TCP on port 1024.
Yes, it does.
Now, my basic understanding of networking, and correct me if I'm wrong, is that UDP is incredibly fast, but it just kind of fires the message into the void and hopes for the best.
That's accurate.
It has zero delivery guarantee, but TCP is the reliable one, right? It double checks with the receiver to make sure the message actually arrived, but that back and forth communication makes it slower.
Exactly. There's a handshake involved,
Yeah.
which adds latency.
Okay, so if I'm running a high-stakes live show, why on earth is this mixer giving me the option to use UDP, a protocol that might just randomly drop a command and mute my lead singer's microphone?
I completely understand why you'd ask that. It seems totally counterintuitive until you look at the physical reality of how human beings actually interact with audio.
Okay, lay it on me.
Imagine you have a custom tablet app, and you are dragging a digital fader up and down rapidly to ride the volume of a really dynamic vocalist.
Like constantly moving your finger up and down the glass.
Right. As your finger moves, that tablet is generating and sending hundreds of OSC messages every single second just to track the smooth, continuous motion of your finger.
Oh, wow. Okay, so it's a massive, continuous fire hose of data. It's not just one single command.
Exactly. It's a stream. So if you are using UDP, which has incredibly low latency, and one tiny intermediate value gets lost in the network.
Like just one message out of the hundreds.
Yeah. Let's say the message for fader position 0.42 gets dropped by the Wi-Fi router. It simply does not matter.
Because the next one is right behind it.
Yes. 1 millisecond later, the message for 0.43 arrives. Your ear will never perceive the microscopic gap in the audio volume, and the physical response on the screen feels instantaneous and totally fluid.
I see. So if you forced that action through the more reliable TCP,
The network might actually pause the stream. It would say, wait, I didn't get 0.42, please resend it. And that tiny delay, that microsecond pause to check the data, would cause the audio to audibly stutter, or the fader to visibly lag behind your finger on the screen.
the pursuit of perfect data delivery would literally ruin the performance.
Exactly. But let's flip the scenario. Let's say you are sending a single critical command.
Like what?
Well, say an automation system in a theater is telling the mixer to load an entirely new scene snapshot for the second act of a play.
Oh, okay, so it's changing dozens of things at once.
Right. You absolutely cannot afford for that single message to be lost in the ether. If it drops, the whole scene is ruined.
Right.
In that case, you switch over to the reliability of TCP, where guaranteed delivery matters way more than a single microsecond of speed. The architecture gives system designers the choice to tailor the network behavior to the specific physical action.
That makes perfect sense. Fast and loose for continuous movement, slow and steady for critical state changes.
Exactly.
Okay, so we've got this incredibly flexible language flying around the network. But if the language is so accessible, that means everyone can talk to it, right?
Right.
So what happens when everyone is shouting at the mixer at once? Which brings us to a massive structural problem in live audio that the sources refer to as state confusion.
State confusion.
Yeah.
Yeah, that is genuinely the nightmare scenario for any audio engineer.
Sounds like it.
Imagine a complex, modern live setup. You have the main engineer sitting at the giant hardware mixing console at the back of the room. You have a second monitor engineer standing on the side of the stage using an iPad to adjust the band's earpieces.
Okay.
And you have an automated touchscreen panel built into the wall for the venue manager to use during the day.
Wow. Okay, so 3 entirely different control surfaces in 3 totally different locations, all trying to boss around the same audio engine.
Yes. Now imagine the venue manager presses mute all on the wall panel.
Uh-oh.
But the wall panel software glitches and doesn't actually tell the iPad. So the iPad still shows the lead vocalist's channel as unmuted.
But it's actually muted.
Right. Meanwhile, the main engineer bumps a physical fader on the hardware console. Suddenly, the mixer's actual acoustic state has changed, but the various controllers haven't caught up. Or worse, they are actively arguing with each other over the network about what the current reality actually is.
That sounds like a guaranteed recipe for terrible feedback, blown speakers, and just very, very angry musicians.
That's the worst.
I mean, if I'm looking at my iPad and it says a mic is muted, but it's actually live to the room, I'm completely flying blind. How does the dMix 128 prevent this total breakdown? Because the documentation heavily emphasizes that it doesn't just treat OSC as some bolted-on remote control feature.
Right. It solves this by operating on a foundational principle called deterministic state. And this is managed by something called the central key store.
Central key store. Yep.
Instead of the physical faders and the iPad fighting over who is in charge, the reality is neither of them are in charge.
Right, really?
Really, every single controllable parameter inside the mixer, every volume level, every EQ knob, every mute switch, is represented by exactly one internal key. And that key holds exactly one authoritative value at any given time. That master list of absolute truth lives deep inside the central key store.
Okay, let me try to make this relatable for anyone who has ever worked in a corporate office.
Go for it.
Think about the dark ages of collaborating on a document. You'd write a draft in Microsoft Word, email it to your colleague, they'd make changes, and they'd email it back as, like, draft_version2_final.
Well, I've been there.
We all have. Meanwhile, you kept editing your original version, and someone else is editing a third version.
Yeah.
Suddenly you have competing versions of reality and absolutely no idea which one is the real document. That's state confusion.
That is the perfect analogy for legacy audio systems.
But the dMix 128's central key store operates more like a live shared Google Doc.
Yes.
Everyone, the sound engineer at the main console, the iPad on stage, the automation software in the lighting booth, everyone is looking at the exact same cloud document in real time.
Yeah.
If one person hits backspace on their keyboard, everyone else sees the word disappear on their screens instantly. There is only one true version of the document.
Exactly. In the engineering world, we call this coordinated multi-client control. Because every device mirrors the central key store. If a proprietary wall panel mutes a channel, the key store updates immediately. Instantly, the key store tells the OSC daemon to push that update to the iPad, and the iPad reflects that state. And the physical LED on the main hardware console lights up at the exact same moment.
That's amazing.
They're never fighting each other. They are all just separate windows looking into the exact same, constantly updated room.
Okay, I'm tracking with the Google Doc analogy, but if this mixer acts like one central document, how does it actually read all the different languages trying to write in it?
What do you mean?
Well, we've got OSC, we've got proprietary systems, we've got web browsers. It sounds like a Tower of Babel situation where nobody is speaking the same tongue. How does the mixer understand it all?
It manages this through something called protocol agnosticism. The dMix 128 doesn't actually treat OSC or any other format as a special privileged control world.
It doesn't.
Nope. It treats all external protocols as mere translation layers. The mixer runs background programs called external protocol daemons.
Daemons like background processes.
Right. There's a daemon for OSC, there's another for proprietary corporate systems like QSYS, and another for web-based commands like WebSockets.
Oh, I see. So it operates exactly like a UN translation booth.
It does. That's exactly it. These demons just sit on the edge of the network, listening for messages in their specific languages. When the OSC daemon hears our earlier example, ///01/mix/fader, its sole job is to parse that human-readable message and immediately translate it into the mixer's internal native language.
And what does that native language look like?
It consists of dot-delimited internal keys.
Right, the internal language isn't meant for humans at all. The sources show that it strips away the formatting and reduces it to something like I.0.mix.
Yep, iboa.mix.
Which sounds like complete gibberish to us, but it just tells the core engine, input 0, mix fader. It reduces a complex network command into a basic internal reflex.
And once that command is translated into that internal key, the dMix 128 treats it identically, regardless of where it came from.
Wait, really identically?
Identically. The core audio engine does not know and does not care if that volume change originated from an OSC message over a Wi-Fi router, a WebSocket command sent from a laptop browser, or a physical human hand moving a fader on the mixer's own expensive hardware surface.
Okay, let's pause and really look at the implications of that, because that's huge.
It is.
Are you saying the mixer fundamentally does not care who or what is controlling it? Does a, $150 Stream Deck macro pad sitting on a desk or a custom tablet app that some college student coded in their bedroom over the weekend, do they have the exact same foundational access to the mixer's brain as the main $20,000 piece of proprietary hardware?
Yes, they
Yeah.
really do. And that is why this level of openness is deeply disruptive to the industry.
I can imagine.
This is the fundamental philosophical difference between a closed system and an open platform. Historically, manufacturers built massive walls around their audio engines.
To protect their ecosystem.
Exactly. They wanted to sell you their specific, highly expensive remote control screens. So they might give you a tiny window, maybe a basic app, but they dictated exactly what you were allowed to touch.
Right, they'd let you move a volume fader, but they'd lock you out of the complex routing or the deep audio processing.
Exactly. They kept a monopoly on the advanced features to justify the hardware price. You were stuck with whatever limited control they thought you deserved.
But by opening the central key store to protocols like OSC, the dMix 128 exposes its entire structured set of objects.
The whole thing.
The sources outline this. We aren't just talking about basic input channels. You have total architectural access to OBUSes, matrix output subgroups, effects returns, and even deep metadata like the custom text names of the channels.
If it has an internal key, any protocol that can speak to the translation layer can control it. It completely democratizes how audio systems can be designed.
Okay, the sheer access is definitely impressive, but I'm trying to picture the person actually trying to build these tools. A software developer building a custom app still has to somehow map a physical finger sliding on a piece of glass to the highly specific, complex acoustic math of a digital mixer. How does this open architecture actually bridge the gap between a generic touchscreen and complex audio engineering?
That is a great question. And it brings us to the real genius of normalized values.
Normalized values. Let's get into it.
When you are programming control systems, there are generally two ways to represent values. You can use real absolute audio values, like programming your app to tell the mixer to set the gain to exactly -10 decibels or set an EQ frequency to 1.5 kilohertz.
Which means the controller itself has to understand acoustic math, right?
Yes.
It has to understand the complex curved math of how human ears perceive volume, what audio engineers call logarithmic tapers. Because pushing a fader halfway up doesn't actually mean the sound is twice as loud to our ears.
Exactly. It requires a lot of specialized programming to get that right. The alternative is to use normalized values, which is just a simple generic mathematical scale from 0.0 to 1.0.
Oh, nice and clean.
Very clean. The dMix 128 heavily supports this normalized control, and it takes an incredible burden off the developers. If you are building a custom touchscreen interface, you don't need to teach your app about decibels or logarithmic hearing curves at all.
You just program the digital fader so that when it hits the bottom of the screen, it sends a 0, and when it hits the top, it sends a 1.
Exactly. And then the mixer itself, which already has all that complex acoustic math built into its DSP brain, it handles the heavy lifting of translating that simple 0 to 1 scale into audio reality.
There's this almost absurdly precise piece of internal math happening here that I found fascinating in the sources.
Oh, the unity gain number.
Yes.
Yeah.
To represent 0 decibels, which is unity gain, the ideal resting place for a fader where the audio is neither boosted nor cut. The mixer internally translates that to the normalized mathematical value of approximately 0.7647058823531552.
It is ridiculously precise. It really highlights the hidden complexity of a digital audio engine. But the beauty is, because the dMix 128 handles that complex translation internally, the person building the OSC controller doesn't have to worry about any of those decimal points. They just send their normalized value, and the mixer effortlessly figures out that 0.764-whatever equates to 0 decibels.
Okay, so the math is elegant and the access is totally democratic. Let's ground this in reality for you. Let's look at some real-world scenarios where this open, multi-client, normalized OSC architecture fundamentally changes the day-to-day life of someone actually running a show.
Good idea.
Let's start with modern theater.
Theater is the ultimate proving ground for this kind of integration. In a modern theatrical production, you often have a piece of software like QLab running the entire show. It's playing back sound effects, triggering video projections, managing complex cues.
All from one computer.
Right. And because of OSC, a QLab queue can send network commands directly to the dMix 128. So imagine an actor walks on stage, the stage manager calls the queue, and the operator hits the spacebar. Instantly, QLab sends an OSC message that triggers a massive snapshot on the mixer. In a fraction of a second, the mixer adjusts 20 vocal mic levels, alters the monitor routing, changes the reverb decay time, while simultaneously the lighting console changes the stage lights.
Wow. So the audio mix ceases to be this isolated island. It becomes seamlessly integrated into the automated, living flow of the whole performance.
Exactly. Everything moves together.
That's the high-end, heavily automated professional side. But this architecture is just as impactful on the complete opposite end of the spectrum, isn't it? Consider a house of worship setting.
Oh, absolutely.
You might have a massive, highly sophisticated acoustic room and a powerful sound system, but on a Wednesday night, it needs to be operated by a well-meaning volunteer who has absolutely zero technical background and gets terrified just looking at a giant console.
This is where the open kitchen concept shines brightest. Because of OSC, the professional audio techs can come in on a Tuesday, perfectly tune the room, ring out the feedback, set all the complex EQs, and configure the routing.
Right, they do the hard work.
Then, they can physically lock that intimidating main console in a utility closet.
Out of sight, out of mind.
Exactly. Using OSC, they build a highly customized, ultra-simple tablet interface just for the volunteers. And this interface might literally only have 3 buttons: main volume, Pastor McMute, and video playback level.
So the professional chef sets up all the complex ingredients perfectly, but builds a tiny, incredibly safe window where the volunteer can only access exactly what they need to serve the meal, with absolutely zero risk of accidentally, deleting the main mix.
And because of that multi-client architecture we talked about,
Yeah.
if the technical director pulls up the mix on their laptop from the back row just to check something, it doesn't interrupt the volunteer's tablet at all.
They both just work seamlessly.
We see this same democratization in live gigs with the musicians themselves, too.
Oh, right, like the monitor mixes.
Yeah. Instead of a stressed-out monitor engineer trying to guess what the drummer wants to hear while mixing 5 other bands, the drummer can just have a tablet mounted to their kit running an app like TouchOSC.
And they just mix it themselves.
Exactly. They are securely dialing in their own personal earpiece mix via OSENs, while the front-of-house engineer is simultaneously mixing the massive main speakers for the audience. Neither one is disrupting or confusing the other's state.
And the barrier to entry to build these workflows has just completely plummeted. You don't need proprietary gear anymore. You can trigger massive show macros with a cheap Stream Deck macro pad you bought online.
Yeah.
You can use generic apps like Mixing Station to get incredible control from a smartphone you already have in your pocket. I mean, the technology is adapting to the user, not the other way around.
Which brings us to the ultimate takeaway from all this material. When you synthesize how the central key store operates with the universal language of OSC, you realize that OSC is not just a remote control add-on.
No, definitely not.
For the dMix 128, it is a gateway. It transforms the mixer from a rigid piece of furniture into an open, network-centric audio platform.
And if you're listening to this, the core insight you should carry with you into your next project or gig is realizing that the future of professional audio control has fundamentally changed. It is no longer about isolated, massive pieces of hardware guarding their secrets.
Not at all.
It's about flexible, multi-client, interconnected ecosystems. The mixer is no longer a physical barrier you have to stand in front of. It's a shared engine you can tap into from absolutely anywhere.
It is a massive paradigm shift. And, if we take everything we've explored today about protocol agnosticism and the central key store to its absolute logical conclusion, it raises a deeply fascinating question about the future of the industry.
Okay, where are we going with this?
Well, think about it. If the dMix 128's giant, expensive physical hardware surface is technically just acting as one of many peers
Yeah.
talking to an internal digital key store,
Right.
and if cheap tools like OSC or WebSockets can access every single parameter with zero latency over a standard network,
Oh, wow. I see exactly the path you're walking down.
in the near future, will a mixing console even be a giant piece of physical hardware sitting out in the middle of an arena taking up valuable ticket space?
Or will the actual mixer just be a software license running on a silent, featureless server hidden away in an IT closet,
Yeah,
controlled entirely by distributed tablets, generic touchscreens, and automated show controllers?
exactly.
So that massive, intimidating table of faders and glowing tape we pictured at the very start of this dive. It might just disappear from the room completely, leaving nothing but the open network behind. Something for you to ponder.